Okay, so now we will solve the problem on the equilibrium of the beams. So what is a beam? So beam is a structural element or the structural member that primarily resists the load applied laterally to the beam axis. Okay, so beams are used to support the superstructures in the buildings. So it carries the lateral load. Okay, so this is the direction for the load. Okay, so here you can observe the beams connected in the buildings. So these are the beams used in the construction of the bridges. So there are different types of beams used in the constructions. So first we have the cantilever beam. Okay. So cantilever beams, they are fixed at the one end only. Okay. So this is called as a fixed support. And the complete beam is overhanging. Okay. So this is called as a cantilever beam. So for the cantilever beam, the support is given only at the one end, and that is called as a fixed support. Okay. Second type of beam, it is called as a simply supported beam. So beam is supported at its both end. So this is called as simply supported beam. So here, suppose this is the beam AB. So at the point A, there is a hinge support, and the point B is the roller support. The next is the overhanging beam. Okay, so the third type for the beam is the overhanging beam. So overhanging means the beam is supported at some midway of its total span, and some portion of the beam is overhanging from the support. Okay, so this is called as the overhanging beam. The next is the continuous beam. That means beam is initially supported at its both the ends, like simply supported beam. Okay, and the problem with the simply supported beam is if the beam, just observe this diagram. Okay, so this is the bridge. So for the bridge, these are the simply supported beams. So at this point, the support is given, and somewhere here, actually, it is not visible. Just imagine the second column is at this point. Okay, so this will become the simply supported beam. So if you observe, just the side view. So this is one point for the support, and this is the second point for the support. Okay. Suppose this span is too long, then there is a possibility that this beam, it will bend like this. Okay. So these two supports, they are not sufficient to restrict the deformation of the beam or the bending of the beam. So some additional supports are given. So this is called as a continuously supported beam. So this is shown here. So these additional supports, they are just used to restrict the bending or the deformation of the beam. The next support we have, the next type we have is a fixed ended beam. Okay. So fixed ended, it is shown here. So this is the fixed ended beam. Okay, both the ends, they are fixed. And then we have the cantilever simply supported beam. So cantilever simply supported beam means for the cantilever beam, one end is completely fixed. Okay, but there is a possibility that if we apply the excessive force on the free end, so this is the free end for the cantilever beam. Okay, then it may cause the bending like this. Okay, so to avoid this bending, its free end, it is supported by the roller support. So this is called as a cantilever simply supported beam. Okay, so for your syllabus, we will have the problem on this first type, which is the only cantilever beam. Then second type, the simply supported beam. Then we will have the problem on the overhanging beams. and last is the cantilever simply supported beam. Okay, so there is no problem on the fixed ended beam. Okay. Okay, so this is the first problem on the beam, that is the equilibrium of the beam. So just draw this. So here in this problem, the beam ABCD is supported at the 2 points. One is a point A and the point B. Okay. So point A is the hinge support and the point D, it is the roller support. And it is loaded as shown in figure. So here we have 2 point loads, each of 8 kilonewton. One is at point B and at point C. Okay. Second load, you can observe here, just take this point as a E. So from D to E, we have the uniformly distributed load. Okay. So this is the UDL and its intensity or the magnitude of this UDL is 15 kilonewton per meter. Okay. So UDL is expressed as an intensity. So this is 15 kilonewton per meter. Okay. And there is one couple present in the system at this point. Okay. So this couple is given as a 20 kilonewton meter. So this is the magnitude of the couple. So your first step, we have to find out basically the reaction at point A and B. So we have to draw the free body diagram. So just isolate this beam ABCD and we have to show the forces and the reactions. Okay. So just draw the beam ABCD. Okay, so when you draw the free body diagram, initially show the forces as it is. Okay, so we have 8 kilonewton and 8 kilonewton at point B and C. Okay, next at this point, so let us take this point as a F. So at point F, we have the couple 20 kilonewton meter. So show that couple as it is. This is 20 kilonewton meter. Okay, next from point D to E, we have the UDL. Okay, so in the last lecture, we have seen how to convert UDL. So we need to convert UDL into corresponding point load. Okay, so conversion of UDL will be, so suppose we have some span and this is the UDL. UDL can be shown like this. Okay, and its intensity is W Newton per meter. So when you draw the free body diagram, we will convert this into a point load. So this point load, this is equal to intensity into the span. Suppose this total span is L. So this is W into L. And it will act at distance L by 2, exactly at half distance. So similarly, here we will show the point load. So this is the F and this is equal to intensity is 15 into its span, this is equal to 1 meter. Okay, so this is equal to 15 kilonewton. So this is the point load and it will act at distance 0.5 and 0.5. Okay, so this is the point E, this is point D. So here now we have converted the UDL into the corresponding point load. Now next is we have to show the reactions at point A and at point D. So A is the hinge point. So for the hinge point, we have 2 reactions. So this is vertical reaction, VA, and this is the horizontal reaction, HA. Okay. So right now we don't know the direction for HA and VA. So just we have assumed positive Y and positive X direction. Okay. Even you can assume negative Y and negative X direction. Okay. Then at point D, it is the roller support. So here roller support, this reaction will be perpendicular to this horizontal line on which the roller is resting. Okay. So this reaction RD, so it is exactly vertical because this line is exactly horizontal. Okay, so this is complete your free body diagram. Okay, now you can show the distance. This is 1 meter. Then here we have the 0.25. Then this is 0.75. So actually this is 1 meter directly. Then this is again 1 meter. Okay. Now next, observe total unknowns in this free body diagram. So here we have HA, VA and the reaction RD. So we have total 3 unknowns. So we must use 3 equations of equilibrium. So conditions of equilibrium, summation Fx0, summation Fy0 and summation of moment 0. Okay. So out of this, which condition we should use first so that we will get at least one unknown? So here we will use summation of moment. So if you take summation of moment by all the forces about the point A. So initially use this condition, then you can find out the unknown RD directly by using this equation, and then use summation Fx0 and summation Fy0. So you can find out VA and the reaction HA. Okay. So take the moment by all the forces about the point A, and from this you can find out the reaction RD. Okay. So when you take the moment about A, you will make this moment 0 and this moment 0. Okay. So you will cancel out 2 unknowns from that equation. So there is only one unknown in this equation, and then you can find out the reaction RD by using this equation. After that, use summation Fx0, summation Fy0, calculate VA and HA. Okay. So try to complete this problem as a homework. Otherwise, we will solve this in next lecture. So we will stop here.